Welcome to In-Memory Techniques for Low Latency Trading. My name is Kevin Goldstein and I'm with Neeve Research. I live in New York City and I have been there for the last 18 or so years, and I've spent the lion's share of that time working on Wall Street, primarily on low latency systems for Wall Street. And that means that I've spent a lot of time on the trading floor. I've ended up developing the habit of speaking really, really fast. So if I'm running too fast through any of this stuff, somebody yell out and I'll try to slow down. Again, so I've worked mostly on trading systems. I've had the pleasure of working on the front, middle, and back office of these systems. I've also had the pleasure of designing a lot of this stuff from scratch, and I've also had the pleasure of being asked to consult on systems that are behaving badly and people want to be able to speed them up. Previously, I've served as the head of the next generation architecture for hedge fund administration system. I've also served as the head of development for a low latency trading shop called Flow Traders, which is one of the largest in the world. Currently, I'm a senior solutions architect with Neeve Research, and this is the next step in my career evolution. These guys are really pushing the envelope of what you can do with in-memory techniques and solutions. So they're coming up with some really, really fun stuff to work on. As the industry is getting more and more comfortable with the fact that you can require low latency systems from other verticals, I find myself giving these kinds of speeches more and more often. For example, I'm giving a more detailed speech of this in New York on October 25th, and I'm also giving an HTAP speech here in San Francisco on sometime in November. Before we jump into it, I want to just quickly define our agenda. I'm not sure if everybody is on the same page of what we talk about when we say trading system, so I'm going to give a quick introduction to that, or more of a primer, really, just to make sure we're all talking about the same things. Now, what I have run across is that all of these low latency systems, however the implementation is, they all share the same concerns. They're all worried about the same stuff, so we're going to spend a good amount of time talking about what those concerns are. And then we're going to talk about the in-memory techniques and in-memory computing and techniques that we use to solve those concerns, mitigate those concerns, or even remove them completely. Then I'll open up the floor for Q&A. One thing that I will point out is that most people, when you hear using in-memory, think of strapping a jet engine onto a car. And I actually agree with that analogy. And in my mind, when somebody says you're strapping a jet engine onto a car, this is the picture that I conjure up. The problem is the devil's in the details, right? And if all you're going to do is strap a jet engine onto a vehicle and you're not paying attention to the details, you may end up with something that looks like this. That is indeed a jet engine strapped to a vehicle. And for good measure, somebody put two of them on there. It's not doing what you want to do. And this is something that you end up seeing in a lot of places where they can't figure out how to get their system to perform as fast as they could, because they're indeed doing in-memory techniques, but without the proper frameworks, without the proper way of viewing the world. You just have no chance of reaping those benefits. So some of that information is going to bleed into this talk. It's not just the techniques, it's some of the ideology, some of the frameworks that are required in order to get this thing to behave the way that you want. Great, so let's just jump into the pool with both feet. And so let's define what a trading system is, right? A trading system at its core, at its kernel, is basically just a system that's taking outside impetus, right? That some people like to call that market data. They're passing that to an algo engine. That algo engine is processing that market data, and then they're passing it to an order router. That order router, in turn, is then sending that to a market for execution or for posting or whatever it is you're going to do. Now, this actually looks really similar to a lot of the systems that exist for the rest of the world. And again, that's why I'm saying the techniques and approaches that Wall Street has developed over the last 20 years are really bleeding into different verticals and different industries. Now, anybody familiar with a trading system is going to look at this and say this is woefully underrepresented. Trading systems are incredibly complicated beasts and include hedgers and regulatory reporting and position management and pre-trade risk and config engines and all this other stuff, and they are absolutely right. In fact, a trading system is a complex ecosystem of components all working in concert toward a singular goal. And if that sounds like the definition of an organic system or a biological system, that's absolutely right. They behave exactly like organic systems. They behave exactly like biological systems, right? So much so that they suffer evolution and they suffer mutation. Pieces of software that started out doing one thing on your particular system end up doing something that's completely different. right? So you have to be able to worry about, to deal with that. But at its heart, if you're able to see through the noise, if you're able to see through all of these things, at its heart, a trading system does this. It receives outside impetus, it figures out what you want to do with that outside impetus, and then it sends orders to the markets and it represents it in the real world, right? All pieces of trading systems share, all pieces of trading systems share one behavior. And it's that they're receiving messages and they're processing that message and then they send that message out. That's what they do. I'm going to start talking a little bit in this example about a basic order router. Those among you may have heard about smart order routers or complex order routers or compound order routers. We're not going to address those right now, but we're going to talk about a basic order router. And at its core, at its heart, what it does is it receives messages coming from a client, right? It then translates those messages and sends it out to the market. And you're right, the word translate is important because it's doing exactly what a translator does. It's taking English to Spanish, French to German, right? Russian to Mandarin. This is what it does. And this sounds like an easy job. It's taking something in, right? Translating it, sending it out, waiting for a response from the market, and then returning it to your client. Well, the complexity of this stuff starts coming in from the fact that you want to be able to do this at speed. And the fact that you want to be able to do this at speed means that you're doing it asynchronously. It means that you're now you receive something in from the client. You're not going to wait until that whole process goes through, right? You're going to pass that off to a different thread, and you're going to continue receiving stuff from client. You need to be able to do this operation hundreds of thousands of times a second. And that information is then going to be acted upon, inspected, and acted upon and sent out to the market. And that response is going to be asynchronous from the market as well. And you sort of have to match up what you're getting from the market and what you're sending out back to the client. Now, again, don't be fooled. Don't be fooled by the simplicity that I say of something that's being translated. While it is analogous to being translated to English or Spanish and things of the sort, that translation, actually just like in any language, as well as on a trading system, is very complicated and deals with a very large state graph. And this is a simple order router. A lot of order routers end up having to deal with baskets, right? Where you're placing, you're treating an individual compound set of instruments as multiple instruments, as a compound set of instruments as a single order. And you have to break that out and send it out into either the same market, multiple markets. You have to worry about times. At its core, every component, every order router is doing this. It's doing a state graph, right? It's receiving messages in, it's processing it, and receiving and sending messages out, and it's matching them back up as it flows through the system. And it has to do this at scale. And that's my primer for the trading engine, right? Like I said, it's incredibly high level. People like to say 20,000 foot. I'm going to say this is at like 50,000 feet or 100,000 feet. This is as high a overview of a trading system as you can get. But like I said before, all of these things are actually, they worry about the same things. And I'm going to talk about the top 3 or 4 things that all low latency trading systems worry about. And I'm going to talk about them in the order of priority. The first and most important one that everybody worries about is performance. What we're shooting for here is the low 50 to 20 microsecond view of the world. We're shooting for 50, we'll take up to 20. If you are responding slower than 20, man, you're out of the game. Don't worry about it anyway. If you can the closer you can get to 5, the better. The problem that when you suddenly start talking about measuring things at 5 to 20 microseconds, you'll set people down in front of a computer and they say, I can tell this is working really fast. Not at these speeds. This is beyond human comprehension. This is, you can't tell if something's working fast or slow or going double the times. So suddenly people get interested into what exactly are you measuring, right? And so what we're measuring in the purposes of this conversation is we're measuring what we call I to E, ingress to egress, right? From beginning to end. And what that means is that we're receiving a message off the wire, those bits and bytes, those zeros and ones, but we haven't deserialized it yet. We haven't unmarshaled it yet. And then we do some kind of processing inside of it, and we're ready to send it out to the market, right? But we actually haven't put it on the wire yet. Right? But it's all ready, it's now serialized, it's now marshaled, it's all in that bits and bytes, it's ready to go out. We're not, in this particular context, measuring wire latency. Don't let that deceive you that people aren't measuring wire latency. In fact, a lot of the big data centers like Equinox, right, they will guarantee that your systems have the same length of wire as everybody else that they do from the exchange. So if you walk into these systems, you'll see these large bands of wires that have been just wound and wound and wound to make sure that you're on a level playing field, that the wire length that you're dealing with and that your competitors are dealing with are exactly the same, and you're not going to have that nanosecond superiority. Right? So wire latencies are important, but for the conversations that we're having right now, we're only talking I to E. Right? So great, we've been able to go out and we've built this system that's working somewhere between 5 to 20 microseconds. Everybody's happy. The next thing that people are going to start asking for is consistency. And what that means is they want your order router to perform as consistently as possible. Your order router has to have the same times, or same response times at 10,000 messages per second as you do at 100,000 messages per second. And this is viewable in life as well, right? If it's Super Bowl Sunday and you go to Circle K to buy some chips and dip or some beer or whatever it is you're going to buy, you don't say, oh, well, it's Super Bowl Sunday. It's okay if the credit card takes 10 minutes to clear. Right? You expect it to take the exact same amount of time as any other time, right? And the same thing happens at Mardi Gras, right? If you see the sea of people down there, same thing. Oh, you don't say, well, there's a lot of people going on, the credit card system is overwhelmed. I'll let it take 15 minutes. No, if it's not working within 1 second, you're going to have a problem. And the same thing is true with trading systems. You're not looking for this linear 45-degree angle as the volume increases, your latency increases. What you're looking for is a flat line. Right? As the volume increases, that line has to stay flat at the same level. And in fact, when that is it's most important when the volume does increase that your line remains flat. And that brings us to our second point, is that we're looking for a really low level of standard deviations. Right? We're really looking for 1 microsecond standard deviation at like 99th percentile. If you're running something along the lines of if you've gotten your system to run at 10 microseconds 99% of the time, but that 1% of the time is taking 1 second, it doesn't matter, you're done. You've got to have a consistent timing. You've got to have a consistent view of the world in order for your system to perform. So great, now we've gotten past the first two. You got performance, you got consistency, everybody's happy, and the next thing somebody walks up and says, well, hey, this system has to be reliable. And say, all right, well, that gets a little bit more complicated. What exactly do you mean by reliable? And there's two breakouts here. The first one is that we're talking about is message reliability. You didn't lose an order. You didn't lose an execution. You didn't lose a confirmation. And there's a lot of reasons that you can lose orders, right? You can be migrating configuration over from one system to another. You could have suffered a catastrophic event where you have a crash of one system, right? Your NICs could be dropping pieces of information because they're starting to fail. You have to have an approach that you can deal with this, where you're not going to be losing messages, right? And this is intimately related with the next one, where you have to be able to survive process and even machine failure. One of the largest reasons that you start losing messages is because you've suffered process failure, right? Excuse me. You've taken off 500 messages from the wire, you haven't started processing yet, and then your machine dies. Well, guess what? You lost those messages, unless you have some kind of approach to it, right? And that's something that you need to think about beforehand. And then lastly, the last thing that people care about, and it's the least important of all, but it's a pretty good one, is we care about complexity. Like I said, these systems are almost biological in nature. Another more technical term of them is they're distributed, parallel, and concurrent processing systems taken to the extreme, right? They are the definition of microservices. And what that means is they grow in complexity just incredibly fast. And so the more simple that you're able to deal with this, the more simply you're able to design these systems, the easier it's going to be for somebody to join into the particular system. It's going to be able to diagnose the system. It's going to be able to add to that architecture and make your particular system better. So let's look at where we are today. This is one of the systems. Is this showing in the front? This is probably something that most of you are very familiar with seeing. And this was actually really good for the first generation of in-memory computing techniques, right? What you have here is you have a shared data store, or so a lot of people call this a data lake, and more often than not, it's some kind of data grid fronting a database, or some kind of Kappa architecture fronting a disk. and it's a shared data store. All data is fed into this particular lake and may or may not become the owner of state. And then you've got these processes down here that are reading and receiving from this shared store. Now, originally, when we were having to read from databases and we were having to read from disk, this architecture found us something along the lines of 3 and 4 orders of magnitude faster than what we were dealing with. So this was great, except that the second you give somebody 3 or 4 order of magnitudes of performance, they say, great, now I want 3 or 4 orders of magnitude on top of that. Right? Now I want something faster and more reliable and better. And guess what? That particular architecture doesn't work for this. Right? Shared data suddenly means contention, data that's under contention. I've got to figure out if you can write to it and you can read from it, or you can read and write and well, he can only read. Like that distributed lock, that shared contention is problematic, and it actually will take you out of the game almost immediately. The other problem that we end up talking about is that these processes, like I said, I'm not sure if you can see the mouse, so I'll try to use the pointer. Right? These processes here get incredibly complicated, right? They evolve into this ecosystem, and in many instances, they mutate into this ecosystem. They're not doing the things that they're originally supposed to do, and suddenly, so there's a lot of places that are doing Monte Carlo simulations and Fourier transformations, right? Figuring out pricing engines, figuring out different channels, doing like some really complicated logic, some P&L logic, right? And suddenly, you're baking all of these relationships into the code. You're actually baking all of this complexity into the code, which makes it hard to understand for anybody coming in, and even harder for somebody to write. Not only do you have to know the business logic now, but you actually have to be somebody who's really good in the field of computer science for distributed processing, parallel processing, right? That becomes hard to do. And something else that you'll find, the more complicated the processing that you're trying to do, the more data that it requires. And the more data that it requires, you're sending it back to the data store, and you're trying to pull more and more information, right? And the more information you're trying to pull, the slower it gets. It's a self-feeding loop, right? Again, this worked out really well for the first gen of IMCs, but didn't really work out so well for the next gen, right? As things got more stringent, as things are expected to be faster, and they're expected to be even more reliable. Something that I almost glossed over and forgot here. There's no real reliability baked in here. Right? If you want to bake in your reliability, you as developers have to think about that. You, as you're already developing a very complicated pricing engine or order router or what have you, market data engine, right? You've now got to think about reliability as well, right? And transaction processing systems as well. So this doesn't work for the next generation of systems. So let's reach into our bag of tricks and see what does work. What can we pull out to make systems better? Well, it should be no surprise that we're going to start talking about memory, right? Based off of the name of the conference, based off the name of this speech, in-memory computing techniques. Memory is going to be one of the things in our bag of tricks that lets us go faster. I'm pretty sure most of you guys have seen this graphic before, so I'm not going to talk about it much. I'm just going to throw it up to say this graphic shows that you can get orders of magnitude of speed increases when you move from SSD reads up to the L3, L2, and L1 cache. We'll come back to that in a little bit. But so we know we're going to be using in-memory techniques in order to get that. And this graph is sort of good to keep in the back of your mind as we start talking about a lot of this stuff. So what else is in our bag of tricks? And this is what I was saying originally, is that we're going to suddenly start talking a little bit about philosophy, right? We're going to talk about how you approach computing. We're going to talk about the fact that if you want to have large volumes of data flowing through your systems at incredibly low latency times, we have to change our perspective from a pull to a push, right? We suddenly have to we have to worry about the concepts of ownership, publication, and consumption. Now, when I'm talking about consumption, what I'm talking about is how do you consume the data in the most efficient manner, right? Let's go through an example there. Somebody says, hey, Kevin, can you buy me a Pepsi? And I say, sure, and I'm going to pull out my iPhone, I'm going to log into my bank, and I'm going to say, I got $50 in my bank, I'm going to buy you a Pepsi. Great. The next somebody else comes up and says, hey, Kevin, I want you to buy me a Coke. And I say, sure, no problem. I'm going to pull out my iPhone, I'm going to log into my bank, and I'm going to say, hey, I have $48, I'm happy to buy you a Coke. Then somebody walks up and says, hey, Kevin, I want you to buy a Fanta, so on and so forth. You can see where this is going, right? Whereas on the flip side of that coin, if every time somebody made a transaction, right, to my account, somebody just hand me a piece of paper and I can look at it. So I'm walking around and I know what my bank account is every single time. I don't have to ask for it. It's just sitting right there in my hand. So somebody says, hey, I want to buy a Coke. Yeah, sure, no problem, right? That is what we like to refer to as data gravity. The farther away your data is from the processor, the slower it's going to take you to process it, right? You have to go and fetch that piece of data and bring it back here in order to process it. You're now acting in a very, very slow manner. The next thing that we want to talk about is ownership, right? So we're going to transfer responsibility of somebody saying, I'm going to go look for that data, to now every single piece of data is going to have a clearly defined owner. And this buys us a whole bunch of stuff. Number one, this buys us data governance, right? When you were originally querying a piece of information, somebody just replies to your query and they say, hey, here's the data that you asked for. Is it correct? I don't know. It's not my job to know if it's correct. This is what you asked for. Whereas now, if there's a clear owner of that data, right? No longer are you just providing data. Before you're getting that data, you're enriching it, you're verifying it, you're making sure that that piece of data, that account number, that trader number, that instrument that you're dealing with, that RIC, that CDAL, whatever it is, that's actually correct and pointing at the right thing before you distribute it to somebody, right? So you're transferring responsibility of the data governance, but you're now also transferring responsibility of how you get that data to somebody. I need to be able to, I'm moving from that pull to that push mechanism. So that owner now is saying how many people are interested in it, I'm going to push it to them. And I need to be able to push it to them in a transparent and free manner. And that's where that publication comes in, right? That's where these communication topics such as pub sub and pub sub and channels come in, where we're going to, you don't want your owner suddenly saying, doing a look, how many people are interested in it? Oh, 48 subscribers to this. I'm going to do this in a hash table and send it 48 times. No. You need to delegate this to your infrastructure, and you want to delegate it for free, right? And that's where proper use of communication channels comes in. So if we go back to this previous slide this previous look, and we take into account and we fold in this concept, right, of ownership, publication, and consumption, you can see that we still have this data lake up here. That's never going to go away. That actually has a vital role in your organization. Excuse me. A vital role in your organization. However, but you'll also see that we suddenly have this data in motion tracked. And the idea here is when you lay data to rest, you slow it down. When there's a piece of data in motion, you want to keep it in motion. With these topics that I just talked about, as the data comes in, as each individual piece of data, you're going to receive it, you're going to curate it, right? That means that you're going to capture it, you're going to refine it, you're going to aggregate it, you're going to verify it, and then you're going to route it to the appropriate person. And that appropriate person, in turn, may look at it and say, I'm the final destination for this piece, or I'm not. I've got to continue moving. I've got to, keep it in motion. I want to get this piece of data to the appropriate user, right? That's that data gravity thing that we're talking about. So now that we're routing data, via transform enrichment and everything, by transform enrichment and routing, right? We're now being able to store your state right next to that particular process, right? And that's that example of having that, your bank account sitting in your hand being updated by somebody else. So great. This is what it looks like in theory. Let's delve in a little bit more and say, how does this translate into the real world? Now remember, we started out with those three things. We said we have a piece of market data, we have an algo engine, and we have an order engine, right? So we're starting out with that piece of market data. Using the publication techniques that I just talked about, right? We're going to reduce the noise that every component of my system actually has to deal with, because we're going to break them out into channels, into swim lanes, right? So now my algo, I just freed up 50% of the amount of original work by breaking these algo engines up into two, right? So not only is my algo engine, it's not just dealing with everything, it's only dealing with tickers going A through M, or tickers N through Z. And on top of that, these algo engines are now only going to be publishing useful, already enriched pieces of data, right? What I like to call actionable pieces of data, to that order router. So that order router is no longer receiving market data. That order router is only receiving actionable pieces of data on top of it. And what does this do? This does a couple of things for me. Number one, it reduces my memory footprint, right? And that reduction in memory footprint opens the door to high availability, because my state is now co-located in the same location as my processor, right? Which means I can suddenly start keeping copies of these things. I don't actually have to have some complicated state being kept in a data lake where my processor in some weird funky state here that may or may not have died, right? I'm keeping the same process in the same state in the same location. And the fact that I can now add high availability to this mix allows me to distribute this onto different pieces of hardware. Right? And the fact that I'm not running it on one giant box anymore, the fact that I'm now running it on 3 boxes means I get to buy cheaper boxes with smaller amounts of memory. Now, let's not forget about the fact that I'm working in that push mode. Right? I'm working, that data owner of that reference data, that data owner of any particular piece of data that needs to filter down to me. We don't want to reinvent the wheel every single time somebody wants to publish stuff. But we don't have to. We use the established channels, the established swim lanes in order to publish this information down. And it will filter down to the appropriate place, to the appropriate person. So that you're already holding on to that piece of state when you need to be able to work on it, when you need to be able to use it for processing. So great. This is what it looks like. This is what it looks like sort of in theory, but more in practice, right? Now let's look at a real picture. This is something that is up and running for one of my customers in production, right? I have changed a little bit about how the order routers work, but this is the basic idea. We've gone from breaking stuff out to 2 servers to breaking stuff out into 6 servers or 12 servers or 20 servers. And being able to break that up brings me a boatload of benefits. But chief among them is I get this symbology flexibility. I can now say, hey, you know, I've got 3 tickers that are the biggest movers that I've ever seen. That's Amazon, Google, and Apple. I'm going to give them their own data routers. And I've got tickers, or order routers. And I've got tickers that are pretty big, but not as big. And I'm going to give them their own. The Qs and NVIDIA are all going to be sitting on the same ones. And everybody else can be hosted on these last 2, right? Or you can do something not so crazy, but you can do something where you have all of the high volume tickers working on the top 60% of your systems, and you've got lower volume tickers working on the last 40% of your systems. And guess what? If you suddenly find out that you don't have enough systems because you have this flexibility of symbology, you're able to add more systems. Right? It suddenly becomes real easy to scale things out. And suddenly, you get to start using the terms, we've designed for scale. We've reduced the hardware risk to 0. Right? One of your systems here fails, and it's really no problem. Your backup on another system is going to pick it up, right? And you're going to replace that particular machine and reconfigure some IPs, and you're good to go. Right? Sorry, I lost my train of thought. The flexibility. Oh, right. Something else that I was talking about, the scaling flexibility, right? Up until this point, we've only been talking about scaling things out on business metrics. But that's not the only dimension that we have to worry about. Other metrics that we suddenly want to worry about are not just tickers, or not just the high volume tickers and everything else, but we may want to start looking at pieces of hardware. We may want to say, hey, this particular hardware that's doing, or this particular process that's doing option pricing can run on hardware that only has GPUs enabled, right? Or in this particular system, we can make sure that these order routers, they're small enough to fit on a NUMA node. Remember, I told you I was going to come back to this. So for one of my customers, when they brought me in a while back, they said, hey, we're dealing with order speeds of just under a millisecond, and we don't know why. We want you to make it faster. One of the first things that I did is I spent a week making sure that I could fit their entire order router into a NUMA node. And that speed went from just under a millisecond to just over 400 mics, right? And that's with almost 0 work to it. That's simply by taking advantage of the hardware that's available to me, simply by taking advantage of those in-memory techniques, right? Right. On those lines of the in-memory techniques, back to one of the hardest things to get rid of that I want to talk about is that reliability. A lot of these systems, or most of these systems, are written out in Java, and that means we've got garbage collections, right? We've got this ugly bandsaw graph coming up and down. And we also see that garbage collection, that stop the world garbage collection is going to impact your CPU. It's going to stop you from processing messages. It's going to do a boatload of stuff. And a lot of developers, I can't tell you how common it is for me to run across Java developers that say, hey, what are you going to do? It's Java. It generates garbage. It's got garbage collections. Well, it turns out there's a lot that we can do, right? We don't have to throw up our hands and say, this isn't something that this isn't something that we have to live with. There's a couple of techniques that we can implement. We can implement pooling. That's actually one of the really good ways to go. Pooling means that you want to stay away from the heavyweight processes or heavyweight consumptions of stuff. You don't want to have allocations of memory and deletions of memory, right? You want to pre-allocate all your memory into a pool, and when you're done dealing with something, you return it to the pool, right? That's that actively managing live objects. You want to make sure when an order has been filled, when you're done dealing with it, when the system has been passed off to a P&L engine, and it has been passed off to books and records, you don't just dereference it and delete it and throw it away. You return it to the pool for consumption. Other things that you can consider are leveraging off-heap memory, right? This is outside of the purview of the JVM. So by definition, it can't be garbage collected. It comes with its own set of problems, absolutely, but this is something that you can do. And one of the big ones, and I'm going to show you a graph in a minute, but one of the big ones is warm-ups, right? A different client actually ended up saying that their quants were broken. And I remember hearing them, and I said, wait, what? I said, you mean your processes, or you've got a bug? And they said, no, our quants are broken. Our models are broken. How's that? Well, it turns out the models work wondrously in the afternoon, and they work miserably in the morning. And we have no idea why, because clearly the math is going to be wrong. And what's happening was they weren't warming up their system, right? So in the afternoon, as your system suddenly got warmed up, right, and your JIT compiler was actually doing what it's supposed to be doing, you ended up having something like 99th percentile of these very low, very good response times. But in the morning, right, you actually had, that was around 80%, and this other 20% is going all the way up into the milliseconds, right? So this is one of those cases where they're saying, hey, our math is bad. And it's not that your math is bad, it's that you didn't take the necessary steps in order for the computer to do its job, right? You didn't warm it up. That was actually one of the favorite lines I've ever heard. Our quants are broken. We need to send them back to school. I think that pretty much brings us up to the end of this particular speech. Just as a sum up, like I said, a lot of these techniques are really bleeding out into the rest of the industry, right? And because of that, I find myself giving these kinds of talks. If you're looking to do stuff that has a very high throughput, that has very low latency, you're looking to build things that are running in multi-agent mode, that are having private state, and that are going to be communicating over messaging, right? You need to be able and to be aware of the impact that you're going to have when processing memory. And you're going to have some kind of strategy for dealing with these zero garbage situations, right? You're going to have to be able to process to be able to handle process and machine failure. You have to have some kind of reliability plan. You have to have fault tolerance, and you have to be able to scale stuff out. You cannot be dependent on machine failure. That machine risk is actually really high. When a lot of times I hear people say that machine risk is not that big of a deal because they're pretty reliable. And that's absolutely true when you're dealing with one server. At one point in my past, I was dealing with 10,000 servers, and we had an entire staff because these machines fail all the time. Metal does corrode. NICs do fail. Fans break, and the machine overheats. And suddenly, you're out of the ballgame if you haven't set up a proper infrastructure. And if you follow all of this stuff, you're going to be able to get some of the better performance that you're looking for. I think that's it. So if you guys have any questions that you want to ask either privately or out of band, please drop me a note. My email is Kevin, one second. My email is Kevin. You can also follow me on Twitter at KevGoal0. And of course, my company's website is listed up here as well. Yeah, right in the back.
Hey, Kevin. You obviously cut your teeth in the worst area. You obviously cut your teeth in the hardest industry in terms of the trading floor because you can't be wrong there. For this audience, what would you, for people that haven't got that kind of exposure and they're just getting started in how to bring IMC real for their organizations, what kind of advice would you give them to just get started so that they can mitigate the risk as they take the company forward?
Right? So you're going to have to look for a partner, look for somebody who was able to understand that and able to figure out what is important to you. right? And if they're not able to solve it, right, they're going to figure out how to solve it. Because if they haven't seen this specific problem before, they've seen very similar problems to it. That would be my answer to that. Yeah?
So you talk about the CPR, consistency, performance, and reliability. Is there any security issues that you have to be concerned about?
Security issues. Well, most of these low latency trading systems are usually running on a closed circuit system, so you don't have that much security issue. You do have security issues on gateways. So a really good example of that, there's two massively different kinds of low latency trading systems. There's going to be one trading system that is run by broker dealers, by market makers. This is their own system, and nobody's getting into that system. You cannot hack that. There's no access to it, right? And then there's E-Trade, right, or Ameritrade. And these are people that scale very, very wide instead of very, very narrow. And everybody's got access to it, right? And so you have to have your security on your entrance into that system. And you also have to be realistic about the fact that you're going to be on the forefront of securing that particular system. And you may end up having to take systems offline in the event that you see some suspicious activity, that you have seen some compromises, right? So what you want to do in those situations is you do want to have that Chinese wall of your trading system versus your access to the system, right? You want to make sure that accounts, numbers, phone numbers, social security numbers are completely separate from your reference data systems that we're talking about, tickers, symbols, and connectivity to markets, right? Those are usually the two biggest kinds of flavors of systems that you're going to find. One accessible to the rest of the world where you've got a very big concern and you've got to have that Chinese wall, and one where it's a closed circuit system. The only way you're getting into that is by like walking into Equinix, right, and plugging in a USB or something like that. Yeah.
With regard to about the process failure and hardware failure, so given that the system that you work on involves trading, so in case of such failure, if you do a retry, then it would have exceeded the allowed latency. So what approach do you use to address the?
That's a great question. Just to repeat the question.
Keep it within the maximum allowed latency.
Right. That's a great question. Just to repeat the question, make sure I understood it. How do you deal with that process and machine failover to deal within the latency specified, right? Is that correct?
Yes.
Okay. Well, the answer is when you are failing over, right, you violate those SLAs. There's no way around it. You will violate them no matter what happens. However, you want to reduce that to a minimum. If you're violating that SLAs to the level of a millisecond here or there, and then you recover very, very quickly, right, you're still in the game. You are definitely you're going to have been taken out. Some of your orders are going to be filled or executed, and they may have moved against you. However, if you can recover within a few milliseconds or, even on the longer end of the spectrum within a few seconds, it's not that big of a problem. The big problem is when your recovery mechanism is something along the lines of 3 hours, right? That's not a viable option, right? And by the way, that question that you asked is not an if, it's a when, right? Something bad is going to happen to your system, and you're going to fail over, and you're going to see these bips, and you're going to be able to handle them, and you have to be able to handle them. The question is mitigating that to the smallest degree, and that has to do with how you set up your high availability. That has to how you set up that recoverability process, right? Rereading, saying, oh, I'm going to have, and I've seen this, right? I'm going to have cron D sitting on my machine that is going to reboot the process, and then it's going to reread from database transaction logs in order to rebuild the data. That's not a viable solution, man. It's too late. At that point, you might as well call up the exchange and cancel all your orders, which actually you should have had cancel and disconnect anyway. But you need to have some kind of solution that's going to be able to recover you milliseconds or at the worst case seconds. But you will suffer blips. There's no way around it. Yeah.
Just continue your discussion. Because when you're talking about in memory, you need to have some ability to persist your data. So, and I completely agree. We can go back to the source system to do. So, what's your option? What's your suggestion? How you persist? Because you look on the vendor, they can persist in the file, can some other database.
As many solutions as can be imagined have been presented, right?
What actually works?
Right. Right, so just to rephrase your question, right, is how do you deal with that high availability? How do you deal with that persistence, right? Because every vendor is going to say, well, we've got a high-speed disk for you, and we've got a some kind of other fancy solution that sounds good on paper, but when you put it to the test, always ends up failing for one reason or another, right? So what's the solution? And the solution is appropriate high availability techniques, right? Being able to treat entire transactions as atomic events, being able to read that in, and before I send that out, I've persisted this. And when I mean persist, I'm talking about the speed of communication and the speed of memory to my counterpoint, right? And my counterpart is on a separate machine, on a separate system, right? So that when this machine, and this has to happen before I acknowledge things coming out, right? So that in the event that I do fail, that somebody does shoot that particular process, this process can pick it up seamless as well. Now, there's no, that's the best and fastest way. However, on top of that, you should be writing the transaction logs. You should be writing to, you need to persist your data as many times as possible. But from a recoverability point of view, from a speed, from a recoverability and a high availability, that's your best option. Making sure, and that's hard to do, making sure that you're persisted to your backup counterpoint. And that's hard to do because a lot of people what they end up doing is they use, and I'm not going to, an analogous to multicast, where the order is delivered to both places at the same time. And then you say, oh, well, we're just going to process them both, but one's going to be marked as primary and one's going to be marked as secondary. And you get skew. You can't do that. It's a great idea on paper, but you can't bloody do it, right? So you have to have some other technique that can do that. Yep. You're next. Sorry. Yeah.
So does the transfer of data between the networks, doesn't it offset the gains?
Well, and this is actually one of my favorite questions too. It depends on what we're talking about, right? It depends on how much processing we're talking about, and it depends on the networks that you're talking about as well. I've found using Mellanox cards and Mellanox cards and, well, you find Arista routers and 29 West or another very low latency messaging system. We're talking about 4 mics for a network hop, right? So if you're doing multiple networks, if you're doing 12 network hops on your way to get there because you're going to pre-trade risk, you're going to position management, you're going to everything else, okay, that's probably not good. You shouldn't be doing this stuff in serial. And that's where you suddenly get into this is working as an ecosystem, right? That's where you suddenly get into this whole thing where one message is actually feeding multiple different systems. And then these things are all coming together at the end in order to feed something, right? That's where you get that force multiplier of systems. But that is architectural complexity that you add in, right? So there's always going to be push and pull between architectural complexity, between methods that you're using, versus being able to serialize and add in simplicity. Yes, sir. This one? Yeah. Right. So the question is, how does the public data or the messaging impact the stateful offering that Neeve has, right? And what we do is we allow you, and this this gets very interesting, is what we do is we allow you to model out both your message and your state using our unique modeling technology called ADML, Application Data Modeling Language, right? And so you're defining what messages look like and you're defining what state looks like. And then you're defining an operation that takes that message and acts upon that state, right? And that state is going to be private to any of your systems, right? That state, again, is because we helped define that model, right? Because we helped define that. We know exactly what your message looks like and we know exactly what your state looks like. As you apply, without you having to do anything underneath the covers, right? Without you having to do anything underneath the covers, as you apply that change to that state, that gets migrated over to your counterpart, to your backup, right? And so suddenly, you don't have, and what's happening here, it's that delta of state that gets migrated over, not the computation. So you're not running in that split brain mode. You're migrating only the changes that needed to be migrated over via a different messaging channel, by a pipeline replication, in order to get that high availability. And that's where you get the functionality of you shoot one of them and the other one just knows exactly where you were. Yeah, so that's the high-level answer to that. You said you had 2 questions, though.
No, I think you answered that.
Okay.
That's fine.
You want to architect all of this stuff. You want to architect as many of these pieces as possible along these lines, right? For 2 reasons. Number one, this gives you, with the microservice architecture, private state, and messages communication, you get an incredible amount of flexibility. So not just does your algo engine die, but I want to test out a new algo engine, right? I can deploy that independent of everything else and bring it up, and I can have it working on an individual piece of state, right? But it's not just your algo engine that has to deal with, that has to worry about these things. Remember, I'd said that, and I'm trying to answer the question. I guess I'm taking the long route. Is there are more pieces than just the algo engine and the order router. Your position management, right? Your pre-trade risk engine, your post-trade risk engine. All of these things should be working under this kind of assumption. Right? Losing a P&L engine, even a post-trade P&L engine, can be just as disastrous as losing an algo engine, because then you can't keep track of what you did. You know, other people are keeping track of what you did, but not you. That's a problem, right? So your entire trading engine, as much as possible, should be designed along these lines. Yes, sir.
You talked earlier about the push.
That's a great question. So the question is, in push versus pull methodology, how do you make it scale as the number of consumers increase? And it's one of those great things of when you're using the technology appropriately, you're delegating that responsibility to the messaging fabric. Now, this is what 29 West does, right? This is what these messaging fabrics do. This is exactly what topics do. You are able to consume hundreds. You're able to consume hundreds or even thousands of these consumers, and you're able to set up hundreds or even thousands of these channels and have them just work, right? So you don't have to have your pushing system have all of that information. You're delegating that responsibility to the messaging fabric as well. One of the difficulties of doing that, right, comes with DevOps. So great, I'm now dealing with, because I'm trying to be really fancy, and I'm going to have one order router per symbol. That means I've now got to stick 3,000 messaging topics on there, right? So your DevOps are going to shoot you. You've got to have some kind of approach to dealing with that, some kind of programmatic approach that's going to look at your particular system and set that stuff up for you. And that's one of the offerings that Neeve system does, right? We have that simple messaging abstraction layer that takes care of making sure that those channels, topics, and queues are set up in an appropriate order. We also translate across different messaging fabrics. So anybody who wants to use this in their current offerings that include Kafka, done, we integrate with that. That include ActiveMQ, done, we integrate with that. 29S, done, we integrate with that. TIBCO Rendezvous, done, we integrate with all of that, right? And if we don't integrate with that, based off of what I just said, we've got a lot of experience writing these adapters. We can write one really fast. Yeah.
Question on high availability. So I think you mentioned you had active set up where you replicate feedback before you set anything out, right? So how does that add to your latency?
Very little. So we do several techniques because our process is actually working because our processes are working single-threaded. It gives us total ordering. And that total ordering becomes important when you're saying, I'm going to be passing stuff off to an individual, to another active, to my backup, right? And it's dangerous to say active-active. I just don't have the lingo for active primary backup that's not active. When you pass that message off, you can park that message and process the previous one. Because everything that's been done to the state is single-ordered, total ordering. You're able to pass that off very effectively and very efficiently. And then we've also got batching watermarking on the way back. If you're able to receive multiple messages coming back, we're able to acknowledge 100 of them or 200 of them or one of them. Right? So it's a minimal, it is absolutely going to affect your systems. Right? There's never going to be anything faster than naked systems, naked ordering, naked algos, naked everything else. But you do have minimal impact in order to get that high availability. We're good. I think that's we hit the time limit. Thank you all for your time and great questions.